We are doing entry ticket for Unit 4, Investigation 1, Lesson 4 together. This is a continuation of what we learned and focused on last week. We kind of went over the patterns of polynomials and their end patterns and depending on their degree and leading coefficient A. So if there is a leading coefficient that is greater than 0 and it's even, it looks like a second degree function. So those have an upward parabola. So it makes sense that a polynomial that has an even degree that has a positive coefficient A would have that same end pattern. Same thing goes for if the coefficient's greater than 0, but if there's an odd degree, so it looks like our third degree function, but our positive third degree function, which makes sense that's why the end behavior is like so. And then on the opposite end, if their coefficient is negative, then it's going to have a end pattern like a downward parabola, because that's the negative version of a second degree function. And then if it has an odd degree leading term, then it's going to have a negative version of a third degree function as its end patterns, as you can see by the blue arrows. I mean, this problem, it's asking you, okay, well, now we're going to make our own equation, knowing what we know about graphs and the patterns that we've learned about them. So it says that it wants you to take a degree 4 polynomial that has exactly 3 intercepts. So if it has exactly 3 intercepts, that means I have 3 factors. So I'm going to pick, in this situation, I have y is equal to x minus 3 times x plus 5 times x minus 9. That gives me 3 roots, because if I set these each equal to 0, I add 3 to both sides, I get x is equal to 3. Set this equal to 0, subtract 5 from both sides, I get x is equal to negative 5. X minus 9 is equal to 0, add 9 to both sides, and I have x is equal to 9. So here I have graphed the x-intercepts. But the one thing I'm missing is it's asking for a 4th degree, and right now I only have a 3rd degree polynomial. X times x times x gives me x to the 3rd. So what I can do is I can say, okay, I'm going to take this factor and I'm going to square it. That way, x squared times x is x to the 3rd, times another x, that's going to give me x to the 4th, which is a 4th degree polynomial. So, thinking back to what happens at each root, depending on the multiplicity or the degree of the root, we know exactly how to graph this polynomial without even using Desmos. So I'm going to do that first. So I have my x-intercepts graphed at x. I'm going to go from left to right. So at negative 5, 0 is a degree 1 multiplicity. But actually, before I even go there, I'm going to say, okay, well, this is a degree 4, and my leading coefficient is going to be positive. So I know that a is going to be greater than 0, and it's going to be an even degree. So I know it's going to have an end pattern like a positive second degree function. So I know that my arrow is going to come up it's going to be going up this way. And at negative 5, 0, because it's a multiplicity of 1, my line is just going to go straight through that root. My next root is going to be 3, 0. And if I look over here, that has a multiplicity of 2. So when I get to this root, I'm going to bounce right off that root. And lastly, x minus 9 at 9, 0, it's going to go straight through that root because it has a multiplicity of 1. It's going to look like a linear line there. So as you can see, my end pattern is going to stay true to what we predicted it would be. And that is the answer to this problem. There is multiple ways you could have gone about this. There's multiple answers to this problem. This is just one of them. Moving on to the next one. It says create an equation of a polynomial of degree 5 that has exactly 3 intercepts, and the graph crosses the x-axis at every x-intercept, and the value of y approaches negative infinity as x approaches positive infinity. So that means as x approaches positive infinity, which means it's going this way, y is decreasing. Okay, so it's probably going to be a downward arrow that our polynomial is going to end in as a behavior, as an end behavior. So knowing that piece of information, and also knowing that this is a degree 5 that has 3 x-intercepts, we're going to make an equation. As you can see, it kind of beat us to the bunch over here. I just picked these random numbers. You could have picked any numbers you wanted, and you could have made your own equation. These are just the ones that I chose. So I'm going to say, okay, well, there's 3 x-intercepts. So I chose x minus 5, x plus 7, and x minus 9 as my x-intercepts. So as you can see, I've already graphed those to the right. So those are our 3 x-intercepts. But we're not done here. It says I need a degree 5, and so far I only have a degree 3. So I can do, okay, well, let me square this one. But here, 2, 3, 4, I still have only a degree 4. That's what we had up here. So I still need to add another degree. So I'm going to just choose to square another one of my factors, right? Another one of my roots. So here I have 2 plus 2 is 4 plus 1 is 5. Okay, so that gives me a degree of 5. If you want to put a 1 there as a placeholder, go ahead. If that helps you visually see that it's a degree 5. Okay, so now that I have a degree 5, and I also know that my end pattern is going to be going towards negative, I can make a couple predictions here. Well, I'm going to go back up to my chart, and I'm going to say, okay, well, I already know that it has an odd degree, so it has to be one of these 2 options. But I know that my end behavior has to end in a downward arrow. So my only option is this one. So that tells me that my A value is going to be less than 0. So for me to make this work, I have to put a negative in front of my polynomial equation. So now I know it's going to go that way, and I know my arrow is going to come from upward here. Now all I have to do is say, okay, well, how does this react at each root? I'm going to go from negative 7, 0, because that's our first root starting from the left. And if I look right here, this root has a multiplicity of 2. So at this root, I know it's going to bounce off. So it's going to look something like this. Then my next root after that is going to be 5, 0. So if I look at that factor and that root, it has a multiplicity of 2 as well. So my graph is going to probably come back around this way, and it's going to bounce off this root as well. Lastly, we have our 9, 0, which if we look at x minus 9, we know that that factor, that root, has multiplicity of 1. So it's going to come back down through that root as a straight line. I need to make sure that this equation is correct. So I'm now going to go on Desmos and just double check my work. So I'm going to say, okay, I have x. This is our graph. I'm just going to pinch just so we can see our curves a little bit easier. That's what I love about Desmos. And I forgot the negative, which is a huge important, because as you can see, when I add this negative, see, it flips the entire polynomial around, and the end behavior is completely opposite, okay? So very important to put this negative here. We did a great job with our graph. It looks very similar, okay? And that's it. You could have come up with your own polynomial, and this is just one of the multiple answers to this, or solutions to this problem. Continue on to the next page. This is page 83. We're going to be dealing with a volume polynomial. So this is a really real world type polynomial, right? So this says the volume of the air flowing into the lungs during a breath can be represented by this polynomial. The volume, V of t, so V is the volume in liters, and t is the time in seconds. So it says use a calculator. We're just going to be using Desmos to help us. The whole entire thing with all the curves that we need. So now I'm going to go back here, and it says, okay, well, what window displays a graph showing all the relevant features of this function? So I need all the relevant features. I need every single curve. I need every single root. So if I'm looking at my margins, negative 10 to 10 on both the x and y axis work. And if you had a graphing calculator, this is when you'd hit second, window, and then you select scale. All right. Now it says, would you restrict your window in order to show the domain and range appropriate to the application? How would you do so? Well, if I were to restrict this window, I would restrict myself to, okay, well, I know this problem is saying it's measuring the volume in liters and it's measuring time in seconds. I know that there is no time that is negative. So if I go to my graph here, I'm going to close off. So I'm only looking at the interval from 0 to infinity. Okay, so I'm really looking at this portion of the polynomial. 0 to infinity. You're talking about an inhale and an exhale, and you're looking at this graph. Let's actually go back to Desmos. This is measuring the time for inhaling and exhaling. You start at 0, starting at 0, you have no air in your system, and you're going to start inhaling. That's when the volume of your lungs is going to keep increasing. So if I zoom in here, I at these values, the volume is increasing. That's the y value. The volume is a y value. Time is the x value. So my time is increasing, my volume is increasing until I reach this point, which is like a relative maximum, right? So that's the maximum. And actually, this is the only maximum if I'm looking at the interval from 0 to infinity. So if I look here, this is my maximum, and I know that at 3.423 seconds, that there is 1.1678 liters of air in my lungs. And then if you kind of like go along this line, it starts decreasing. So as time keeps moving on, the volume in your lungs keeps decreasing. So as I hit this x-axis at this root, which they tell me it's at 5.3380, so at 5.338 seconds, there's no more air in my lungs. I've inhaled and I've exhaled. It says estimate the duration it takes for the inhale and exhale. I'm going to say, okay, well, it's probably going to be this, okay? This area. That's probably the duration of the breath, a single breath. Then it says, okay, well, using the zero feature of the calculator, determine the exact duration. We actually have, and again, it's of one full breath. So since we actually have Desmos in front of us, and it tells us the exact intercept, we know that at 5.338 seconds is exactly when we have inhaled and exhaled fully. So, okay, well, at what time during a single breath did the maximum volume of air enter my lungs? The maximum value of air. So if I'm looking at the maximum value of air, you can look at this graph or this rough graph or the one you sketched. I'm going to do this one first. So I'm going to write in blue. I'm looking here at my inhale and exhale. And as we talked about here, at our maximum point, that was where we inhaled and we're starting to exhale from that point. So at this point, and also keep in mind that the y value is measuring the volume of air. So as I keep going along this line, the maximum value that my y has is at this maximum point, 1.1678. Use the graph, estimate at what time during a single breath did the maximum volume of air enter the lungs. We discussed that. It was at this point. And that's what we estimated. So I'm going to put a blue star there. Then it says, use the graph to estimate what the maximum amount of air in the lungs measured in liters. So it's asking for, okay, what was the maximum of air in lungs? So we're looking at this y value. So we're going to say it was 1.1678 liters of air in your lungs at the maximum. But it says using the maximum, compute the exact time when the maximum amount of air was in the lungs and at what volume the air was at this time. So this is actually referring to the same exact point. So it's just asking you it in a different way. Why I wrote this here, and it's asking what time, and we know that this is the time and this is the volume. This is the V of t. So we know that at 3.423 seconds that there was 1.1678 liters of air. The next page is a very similar problem. And it asks you very similar questions. It's just that you have a different polynomial. So in this situation, you have the profit, P of N, which is in millions of dollars, and the production of MP3 players. Actually, graph it first. We have using my zoom in and zoom out functions on Desmos. So I'm going to zoom in, and this is my graph. These are my x-intercepts, and this is our graph. I'm going to do a little rough sketch of it on here. And it asks, well, what would you restrict your window to in order to show the domain and range appropriate to this situation? So we know that, again, we're talking about profit, and we're talking about millions and millions of MP3 players being produced, okay? So again, we can't really look at the negative side. We have to limit it from 0 to infinity because you can't make negative objects. That's just not a thing. Just like negative time, that doesn't exist. So we're looking at this interval, and this is again for my x values. It asks us to draw the graph, and I just drew a rough sketch of it already, so that's all you need to put there. Now it asks you to estimate at what level of production did we start losing. I'm going to go back to this graph so I can touch this and look at my X and Y values. So this is at 0, so no production, no MP3 players, no profit, okay? So the more MP3 players that we produce, the more profit that we get. We keep increasing, and then we reach this maximum point, right? Before we start decreasing again. And as you can see, that's what the rest of the remainder of the graph does. It decreases. So at this point, which is our maximum, is when right after that point is when we start to lose money. My profit starts decreasing, and so does the number of MP3 players that I produce, until we hit 0 and we have no production and no profit again. It's asking, okay, well, how did you determine it? Well, I looked at the maximum. The company started decreasing right after, so that was when they started losing money. That was their peak production and profit, and then they started decreasing again. So they were doing really, really well as a company, but then they kind of started failing, right? Then it says, okay, use the computation of the feature to get the exact level of production. Well, that's exactly what we would put here. It says, give a plausible reason why the profit would be negative after that level of production that we just talked about. I'm going to let you answer this on your own, and I'm actually going to ask you about that in class to see what ideas you might have, and then we're going to have a little discussion about it. Number 6 asks, okay, well, what level of production should this company stop at in order to ensure the greatest profit margin? And again, explain how you obtained your an answer. So looking back to this graph, again, we hit our maximum point, and then we started decreasing. So why would we not, instead of decreasing our profits and our production, we could stay at this exact level of production and profit? That was our maximum profit anyway. So I know that at this point, I should stop. And I'm just going to underline this and put a little star here just to not have to rewrite it again. Then it asks, if the company predicted a profit of $60 million to their shareholders, will they be able to satisfy their shareholders' expectations? Well, if it says 60 million, you have to keep in mind that in the problem it says the profit is in millions, and the production of MP3 players, it's also in millions. So if they tell you that the profit, which is the Y, this is our Y value, so I know that N is equal to 60 because it's 60 million, and I know it's in millions already, so I know my N value has to be 60. So it's asking, will it be able to satisfy? If I go back to my graph here, I'm going to put a line at Y is equal to 60, because that's when the profit would be $60 million. As you can see, this straight line does not intersect with our polynomial of our profit, okay? So that means that we can never reach it. It's just not attainable, because at this maximum point, that's when our production starts to decrease again, and we never are able to reach that $60 million of profit. We only reach a profit of $52 million, okay? Not attainable, which means not achievable. All right, and we're going to actually, for an exit ticket today, be doing a very similar problem that just has 4 questions to answer along with the graph. All right, and we're going to go over that as a class together.